Today I'm going to introduce our speaker. He is currently a postdoctoral fellow over with a joint appointment in the University of Washington Astronomy Department and also at Western Washington University. He did his undergraduate degrees here at the UW, then went to San Diego State for a master's degree, and then came back to the UW to do a PhD before going somewhere else to do a postdoc, and then come back to sort of do another postdoc and then transition into a research position. So today he's going to be talking about this feature or star referred to as Tabby star. A lot in the news about what was going on with it, and he'll give you some of the discoveries and the research that is being currently done.
Excellent. So we can figure this out here. How's that? Can you guys hear me? Yes, no, nod, knowingly? Perfect. All right, I'm going to talk about what I have dubbed the most mysterious star in the universe. And you see a lot of headlines, especially about astronomers, because we, study the cosmos. You see a lot of headlines that are like, scientists don't know, or they're baffled, or they're stupefied, or whatever. A lot of ridiculous language about, scientists not knowing things. And I want to just give you the punchline. We really don't know what the story with this star is. So I'm going to show you how we found it. I'm going to show you what we know about it. I'll show you some of the ridiculous theories that have come up and made lots of headlines. And so you can tweet about that. And then I'll level with you and say at the very end again, we really don't know what the answer is. I'll give you our current best guess, which is literally the best guess as of a couple months ago. And what's so awesome about this object is it's probably not something crazy like aliens, but whatever it is, it's new. And it's neat to have a data set that gives you something that's truly new, not something that was theorized or there was a couple found in the 1800s. This is new. Okay, let's go to half. There we go. Okay, so the story starts really in about 2009 when we started looking in great detail for extrasolar planets. These are planets around other stars, right? Extrasolar, exoplanets. Planets. The goal is to find a little blue dot like this, which you might recognize, around a star that looks like this, which is a picture of our own sun. This is not to scale. Or you would be cooked like a microwave burrito. The old way, and this is old as in when I was a kid, the old way of finding that works. The old way of finding exoplanets was through the so-called radial velocity method. And maybe some of you have heard about this. The idea is that as the planet is orbiting its parent star, it puts a little tug-of-war on the star and causes it to wobble sort of in a little circle, back and forth from your line of sight. And so when the star is moving towards you, the light that we see is blue shifted. And when it's moving away from us, it's red shifted. Now, you are all familiar with this idea, the so-called Doppler method. When you hear a siren go by, as the ambulance is coming towards you, the pitch goes up. And as the ambulance goes away from you, the pitch goes down. This is the exact same property, but behaving with light, the Doppler effect with light. And this was known to work. Here is the very first detection of a planet. This is 1995, so not that long ago in terms, right? There's about as old a detection as probably most people in this room. A Jupiter mass object orbiting a solar-type star. And this is the actual discovery, this little curve. So this is the light, this is the velocity, or the speed of the light getting redder and bluer and redder and bluer and on and on and on. It's folded here about its sinusoidal period. This has a velocity of 50, plus or minus 50 meters a second, something like 120 miles an hour. So any of you that have been on an airplane have gone faster than this. Probably maybe a couple of you who've been in a motor vehicle have gone faster than this. 120 miles an hour is fast, but not that fast. This is what a star, this is what we call the reflex motion of a star, moving back and forth from the sort of teeter-totter of a planet going around it. So we're not seeing the planet, we're seeing the star moving back and forth. This kind of detection is extremely hard to do and very expensive, because you have to stare at a star and try to measure the change in the star's motion down to fairly slow speeds. Now, if you wanted, this is a Jupiter-sized thing. If you want to detect an Earth, you have to detect something that's moving about this fast. The actual entire star will move this fast. And if you want to detect an Earth-like planet in an Earth-like orbit, you have to measure something that's moving this fast over a year. And so this is a period of a few days, lending us to the term hot Jupiter. This is not quite to scale, but this is closer to scale, where we have a Jupiter-sized thing that's sitting absurdly close to its parent star. So this thing orbits with a period of a couple days. So its year is a couple of days. That's kind of ridiculous. This was totally unexpected in 1995. And so this discovery launched the era of exoplanet discovery, exoplanet searches. Now, finding things like this is very expensive and slow, and your sample is biased towards the absurd things like this, giant planets where they don't belong, instead of Jupiter out where it belongs, we think, in the outer edge of the solar system. And so we need a method that is tuned to find Earth-like planets, where you don't have to wait and watch tiny little motions in velocity space. You want something that stands out in brightness. And that's where we get the transiting method. And this is what we're going to talk about for the rest of the talk here, the transiting method, where a little planet crosses in front of its parent star. Okay, now this is drawn to scale with a giant planet. This would be a very, very big planet. But you see the brightness of the star plotted here against time. And if there were no planet, it would just be flat. But as the planet comes in front of a star, you get this dip, this so-called transit dip. And this is the magic that we're after, is looking for this little dip right here, once a year around that star. Yeah, okay, here's a cheesy animation version of that. That's some sweet graphics there. As the planet moves in front and you see a little dip in starlight. This is a little animation. This is not real data either. Let's go back to that's prettier. Now, the bigger the planet is relative to the star, the deeper this transit is, right? That's pretty intuitive. If you block more light from this star, you get a bigger dip right here. And conversely, the smaller the planet is, the smaller this dip is. To find something like the Earth, you'd want to find something about the size of this laser pointer crossing this star once a year. And the dip only takes about an hour and a half to cross. And so you have to stare. You don't know when this is going to happen. You don't know what hour and a half in the year this is going to happen. So you have to stare with an unblinking eye all year long at this star, hoping to see a tiny little dip from a little dot crossing the surface. That's the goal. And so to do that, in 2009, this is where our story really begins, NASA launched this spacecraft called Kepler. Kepler is about the size of a small bus, maybe a large truck. It's not a very big telescope. It's not as powerful as the Hubble Space Telescope. It was much cheaper than the Hubble Space Telescope, thankfully. And its job was to stare at one patch of sky, that patch of sky, for 4 years with an unblinking eye, just staring, taking pictures every 30 minutes or so, every 30 minutes for 4 years. Now, it's in space, right? You don't have to worry about the sun coming up or weather messing you up. You can't see the stars if there's clouds. This telescope just points at this patch of sky for 4 years. And it studies about 200,000 stars. Now, why 4 years? Because if you only see one dip, you don't know what the orbital period is. You just knew that you see one dip. So you have to wait an entire year to see the second dip and say, I think we found something at the right orbital period. But you have to find a third dip, there we go, a third dip to prove that it is periodic. So you need 3 dips, and if you want to find an Earth-like planet, that means you need 3 years. And they built a little buffer in, just in case they found things that were longer, 4 years. And that's what they did. Okay, here's a picture of the camera. This is based on the same technology that the camera in your iPhone is based on. In fact, the chips in your iPhone are direct descendants of the chips that these were built on, only these are slightly larger. This camera at the time was the largest camera ever built and launched into space, and you can see that it's so big that you actually have to make it curved to account for the change in focal distance through the optics. So this is a really cool feat of engineering to build this giant camera. And then, of course, launch into outer space is no slouch either. And a year later, or year and a half later, January 2010, they showed the first results. And I was lucky enough to be there in Washington, D.C. I watched this talk, and it was one of those moments where you could just feel that the whole world had changed, that the whole field of astronomy and exoplanets had changed. Because they released the first images, the first data, and these 5 here are real data of transits. So you can see these tiny little transits and little animations to scale of the planets that you would see. But again, this was the first year of data, actually the first few months of data. This has orbital periods of 3 days, 3 days, 5 days. This is not what we're looking for. You would not want to live in an orbit 5 days away from the sun. Mercury is 88 days, 80 odd days away from the sun, and its orbital period is 80 days from the sun. And it's a pretty toasty place to be. You don't want to live there. You don't even want to live at Venus, which is about 200 days orbit. We need to live out here where the weather is nice and we don't get cooked and we can hold on to an atmosphere and all those pleasant things that make life worth living out here at 300 or so odd days, 365 days, right? So 5 days is still really, really close. And these are still very big planets. This right here is starting to approach what we want. This is like a super Earth, we would call it. It's bigger than Earth, even though the scale is very small. It's bigger than Earth, but that's what we're after. This is how we used to make pictures of the solar system 200 years ago. You would put a little like crank on this, and you turn the wheel, and things would spin. And you can imagine like here's Saturn, the moons that spin around. Here's Jupiter right here, things that spin around. This is called an orrery. This is the orrery, the digital version of the orrery from Kepler. This is an animation created by one of the grad students here at UW. Here, we'll go to all off, just for the ooh-ah factor. This is an animation of, about halfway through the mission, all of the planetary systems that Kepler had found to scale with the solar system. So you can see there's a few. So this outer ring here is, I forget, I think this ring is maybe Earth's orbit. And you can see most of these things are orbiting much, much tighter. Lots of things at a few day orbits. Let's see, no, Mercury, Venus, Earth, Mars. Ah, that's Jupiter. There we go. And that must be Saturn. So that's pretty cool. Kepler was wildly successful. Kepler was able to find thousands of planets. Before Kepler, we had a sample of planets something like a few hundred. After Kepler, we have now more than almost 4,000 planets that we've discovered just from Kepler alone. Okay, Kepler, awesome. Thumbs up, tax dollars well spent. We discovered lots of planets, and there's tons of cool science that we set out to do. But that's not why I'm here today. I'm not here to talk about the cool things that we expected and have been able to do. I want to talk about the weird things that Kepler found, the strange things, the things that make you go, wow. Here's a few of them. I thought, as a scientist, I thought this was really cool. Kepler 9, discovered early on, they numbered them in order in which they were discovered, so Kepler 9 was an early one. It was a multi-planet transiting system, which meant multiple planets, like our solar system, in this solar system around another star. Many planets, and they had different orbital periods. There was a super Earth at 1.6 days. That's too toasty. There was something else, they weren't sure how big it was, at about 20 days, and another planet at 38, 39 days. Okay, these are all really close. 39 days is still a lot shorter than 80. But what's cool is we can start to see they have different depths. So this one, you have to be as close as I am to see there's a tiny little dip right here. But that's the Earth candidate. This one and this one, right? So this one is larger than this one. And what's cool is they don't exactly transit the star at the same place. So this graphic here is to scale. Okay, so if you were to zoom in with some imaginary giant telescope and look at a picture of the actual star, you can see that the nearby planet, the blue one, transits right across the middle, and these other two are kind of offset just a little bit. So we get some sense of the geometry of the entire solar system. We know in our solar system, all the planets, with the exception of like Pluto, which is like not a planet, but it's still kind of a planet, they all orbit in like this flat plane. They all orbit along sort of the same disk in the sky. And this is our first indication that there are other systems whose planes might be slightly misaligned. I think that's pretty cool. One of the more fun things that it found was circumbinary planets. This also was totally not predicted. So what you have here, artist rendition, what you have here is two stars that are orbiting each other in some tight, we call this a binary system, a binary star system. And out here, hanging out outside of those two stars, would be a planet orbiting out here. That's kind of cool. This graphic is okay. This one is a little better. And this is like something you might be familiar with, right? And the idea that there would be two suns in the sky, right, if you were on this planet. Okay, so I said it wasn't predicted. And by that I mean scientists didn't think this actually happened. This was the realm of like science fiction. Like, oh, what if you had a planet around a binary star? Wouldn't that be cool? Nobody thought that the planet would actually be stable and could orbit there stably. And in fact, we found dozens of these, which is really neat. Now, we haven't found any that were the right size. We haven't found any Tatooines in the sense that the ones we found have all been like Jupiter-sized things. And they haven't been in that sweet sort of Goldilocks zone. Again, that 365-day orbit where water is liquid and pleasant and not, your surface isn't just molten lava or just ice. They've all been out on sort of the ice end where everything's way too cold. But there is some hope, a new hope. Sorry. Here's something that I've worked a lot on. I think this is really cool. And we expected this, but we didn't expect it to be as fruitful as it was. Kepler was able to measure stars actually spinning, actually rotating. We know the sun rotates. Galileo was one of the first to actually observe this with a telescope, which of course I have to legally say, don't point a telescope at the sun because you will burn out your eyeballs. But if you put a really strong solar filter on that telescope, you can look at the sun. And if you go and look at the sun for days and days and days, you can actually see the surface turning. The sun turns about once every 25 days. And that's been known now for a few hundred years. But for Kepler, that measurement was very hard. Very few things you could measure on a star actually indicated that it was rotating. Kepler is able to measure the rotation of little dark spots. Okay, this animation is grossly exaggerated, this big spot rolling in and out of view on a star. But you can see the brightness, or flux as we would say, changing as a function of time. So when the spot is away from you, it's bright, and when the spot rolls back into view, it gets faint, and the process begins again. And you're looking for this little sine curve. And here are just 4 actual pieces of data, of Kepler data from the first month of data, showing 4 different sine waves, or quasi-sine-like things. But this is actual data. Here's one rotating at about 10 days. Here's one like the sun at about 20 days. Here's one that's totally bizarre, which I spent a lot of my life working on, with a rotation period of about a day. 20 times faster than the sun. That's pretty wild. And it turns out when stars spin differently, cool things happen. Science happens. This, I think, is really neat. And then we found Tabby's star. This is the headline from the actual paper that was published in Nature. This was the 10th paper in the Planet Hunters paper series, as they were titling it. This is the phone number, the catalog, Kepler input catalog, number 8462852. Now we just call it Tabby's star, Tabitha Boyajian, or Boyajian star is probably more appropriate. And the title was really WTF. Because that is what the conclusion of the paper was, like WTF is with this star. So let's jump in. Oh, and cool to note, Daryl LaCourse, for example, is an amateur astronomer who lives, I think, in Everett. And a bunch of other people on this paper are amateur astronomers. We'll talk about that point again, but this star was discovered by just people, enthusiastic people who were by hand going through the Kepler data and looking at things and saying, what's that? What's this? What's that? And they finally got to one where Tabby was like, I don't know. And that's where it's been. Okay, so this got a lot of press. The Atlantic gave it, I think, pretty reasonable coverage, the most mysterious star in our galaxy. That seems reasonable. In fact, that's what I titled this talk. have spotted a strange mess of objects whirling around a distant star. Maybe. Scientists who search for extraterrestrial civilizations are scrambling to get a closer look. Sort of. It got a Twitter account, and it got a Wikipedia page, so that was cool. So it's in sort of the pop culture now. You can tweet at it. It will tweet back at you, which is kind of fun. And then other people covered it as well, right? And this is the publicity as a scientist you kind of worry about. On the one hand, universities tend to really like this because people get excited and want to come to talks or want to donate money, and you get lots of publicity. On the other hand, it's kind of Looney Tunes, right? Like this graphic right here is showing something that looks like straight out of Star Wars. This spaceship, I don't know what this star is. Like there's another star and another star. I don't know what these are doing. And then there's the spaceship, which looks like it's kind of like out of Firefly. Right? Like you worry about this because it's going to give people the wrong impression. Then you're sitting on an airplane and be like, yeah, I'm an astronomer. I study the stars. Have you heard of this Kepler thing? And they're like, oh my God, you're the one that discovered Firefly. And you're like, no. And then you spend the whole flight having to like walk people back from the flat Earth. You worry about this kind of publicity, right? Here is the actual discovery. This is, I think, figure 3 from this paper. You can go download it. This is the actual discovery. All right, now think back to our model of a transiting exoplanet, right? The starlight is flat because the star is just doing its thing. Then the planet moves in front of the star, and you see this symmetrical U-shaped dip. And then it comes out as the planet moves on its way. Once a year, it comes around and does the same thing. You're now all experts at transiting exoplanets. None of these look like an exoplanet transit. We can all agree, yeah? None of these look like a U. Some of them look like W's. Some of them look like, I don't know, some kind of asymmetric V. I don't know what's going on with this. Like this is like the Batman symbol or something. What is this? Remember we said if a planet is bigger, you get a deeper transit, okay? So the depth of the missing light, we can directly relate back to the size of the thing that's blocking the planet, right? Very simple geometry here. The bigger my head is, the more the projector light I obscure. So if we were to map this back, you would end up with a very, very, very strangely shaped thing going in front. There's no thing in nature that we have that would make this kind of signature. You can see some of these features kind of look similar, like this kind of looks like a, I don't know, like a bat or something. And so does this one. Oh, actually, I'm sorry, that's the same feature. No wonder it looks the same. This is the same one zoomed in. Yeah, that's right. Why did they plot it twice? That's strange. Okay. Some of them look similar. That's my point. This one, 1, 2. This one, maybe 1, 2. This one, just 1. Very smooth. Who knows? And that's what the authors left it. They said, this is nuts. We have no idea what this is. What we do know is that these features, these 3 features, there's a few more that they highlight in other figures in the paper. There's a few more that kind of look similar. They don't repeat, right? There's no pattern. It's not like the Earth going around the sun. Once a year, you'll see that symmetrical, beautiful transit dip. Once a year. Even the hot Jupiters, those wild things that are at 3-day orbits, they go around, it's like a clock, right? This 4 years of data, this doesn't repeat itself. So you can say, if it's periodic, it must be longer than 4 years. That's all we can say. If there's a period, it's bigger than 4 years. Shrug. What's really troubling about Tabby's star, or Boyajian star, is it is a totally seemingly normal F-type star. What's an F-type star? F-type is just shorthand for its temperature. It means it's between 6,000 and 7,600 degrees in the Kelvin scale. It doesn't matter. The point is, it's normal. There's nothing else unusual about it. The sun is a G-type star. It's the next class cooler. There's your trivia for the day. Totally normal star. So how, from a normal star with nothing else unusual about it, do you get these bizarre dips? This is the great mystery. Oh, let me back up. One more thing about these that is worth noting. not only are these dips really bizarrely shaped, right? Like the shape in time is very strange. But if you read this axis carefully, okay, so 1 means 100% flux. This dip and almost this one reaches 20%, so 80%, 20% of the starlight being blocked out. And this one is 15% of the light being blocked out. Like whatever is obscuring this obscures 20% of the light briefly. That makes it enormous, right? That makes it multiple times bigger than Jupiter. Like we have no idea what that could be, and also have this shape. This isn't just like weird, like somebody dropped some loose change out there or something and it's passing in front of a telescope. This thing's huge. Whatever this is huge. All right, the star, seemingly normal. It's a good mystery. Okay, and then the plot thickened. So here is, in gray, here is the data from the Kepler mission. Here's that 20% drop, blah, blah, blah. Here's some more of those drops. And what they realized when they studied the long-term variability is that the star actually, over the 4 years, faded by 3%. So not only are these short time scale weird dips going on that nobody understands, but now there's also this 3% fade. This was not realized until after the Kepler data was finished, and after the Kepler mission finished its 4 years of staring. All right, yeah. Time, 0, 1600, so about just over 4 years, right? And like, the sun does definitely not change by 3% over 4 years. Nothing on the sun causes it to sit there and slowly get fainter and fainter and fainter. Okay, now you wouldn't notice if you went outside, like if the sun was 2% fainter or something. But if this continued, right, over your lifetime, you'd go outside. When you were born, it would be bright. When you were old, it would be faint outside, right? If this continued, this would be like catastrophic. 3% fade over 4 years is nuts. So the plot thickened. And then after the Kepler mission finished its 4 years of observing, we came through with more telescopes from the ground and said, what is this star? And we continued to study it. And so here is, this is 2017, just 1 year of data from 2017. And you can see the star is continuing to do very odd and misbehaving things. None of them are at that 20% level. These are all at sort of like the 2% level. They're smaller, but equally mystifying. None of them look similar. They don't really appear to look like the previous events. Totally mysterious. What is going on with this star? So, to summarize the mystery, as we have found it to date, there are very short period, say, timescales of a few days. Remember, that's still longer than the hour or two that the Earth takes to transit, but still we'll call that short. Few day timescale, very deep fading, dimming things, which are unexplained. And then equally mysterious, though a little less captivating, long timescale, slow fading, which is like unconstrained. Does it keep going? Who knows? Two parts of the mystery, equally compelling. All right, so being a scientist, you need some kind of model or theory or plausible explanation to explain this. And the best theory is the one that can explain the most of the observables with the fewest free parameters. Right? So you could theorize that, well, what's going on is there's a million refrigerators in orbit of varying sizes, and you just got to put the right refrigerators at the right orbit, and you'll end up getting this signature. And indeed, with a million free parameters, with a million refrigerators of varying sizes, you could get it to do this. That is an implausible explanation, though, right? Like, there's no reason to believe there's a million of anything like that in orbit. So what is it? Or, equally valid, what isn't it? Again, spoiler, it's probably not aliens. All right, right off the bat, we can rule out the thing that I spend most of my time looking at. It's probably not rotation. Okay, and the first hint is this does not look like a sine wave. So bravo to those paying attention and notice that doesn't look like a sine wave. And there's really no explanation of things that would look like this and evolve and disappear rapidly. Okay, so it's probably not rotation. But that was a good thing to rule out. And more broadly, it's probably not something on the surface of the star. We can pretty much rule out that it's not something on the surface. It's probably external to the star. It's probably something moving in front of the star and blocking the light temporarily. The very first possible explanation that was put forward by Tabitha Boyajian and her co-authors when this came out was that it could be a series of comets. So here's an artist's rendition of like, they called it a swarm of comets, like, cometary bees or something, that are passing in front of the star. Now, comets, here, we'll go to nap time mode here. So if you've seen a picture of a comet, they have these big tails, right? And these tails are due to the star vaporizing material on the surface and causing the material to fly out the backside as the comet's moving forward, right? And so the idea would be these things have these big, long, extended tails, and that gives you these weird transit shapes, right? So the tail is kind of like flying out the back end. So when except for it doesn't really work. There we go. It doesn't really work. Like these things, like what kind of comet would have tails going out the front and back? Like that doesn't make any sense. And none of them really look like comets. They don't look like anything comets we've seen in our solar system would look like. Never mind the fact that, again, I'll remind you that you need 20% flux dips, 15 to 20% flux dips. These would have to be comets that are bigger than Jupiter. All right, well, that's bothersome. And that still doesn't explain why it's slowly fading. So that's no good. People got a little more creative. They said, well, maybe there's some kind of like disk, like a funky disk. Like, again, think back to our solar system. All the planets orbit around in kind of a disk-like shape, like the plane of the solar system. And so maybe there is some plane of stuff, of like cosmic garbage floating around here. And maybe it's like elongated or warped or something, and so it's kind of, as it passes through, as it rolls around, you get, maybe there's a comet in there as well. You get all the weird brightness variations. And this is not impossible. This could work. But it has to be very dynamic. And by dynamic, I mean, like you need something like this. This is the idea that it is a planetary explosion. Like maybe two planets ran into each other, and one of them had its top blown off like this. Kaboom. That's the sound they make. And then that debris is orbiting around, right? So there's some kind of very violent, large event, and maybe we're seeing that debris spin around the star. And maybe that debris is complicated. There's other little chunks and bits out here. And this is not without some merit. We think our moon formed this way. So if you've ever wondered where the moon comes from, the best model, the best explanation is that there was a big rock, another planet, early in the solar system's history, the size of Mars, not an insignificant rock. And it ran into the Earth on one very unfortunate day. And it caused a giant, massive explosion of material, and out of this came the moon. The moon is smaller than Mars, so a lot of that material landed and settled back on Earth. Earth's surface was probably totally wiped out. This, of course, happened very long ago, like 4 billion years ago, long ago. And then the moon was like the leftover debris recoalesced out here in that nice, tight orbit. That sounds totally wild. Like, why would we think that's the case? But when you go to the moon, and remember, people did at one point, before I was born, people went to the moon, and they brought rocks back. And those rocks look like the rocks here on Earth. They're chemically similar to the rocks here on Earth, except for they don't have all the sort of biological indicators, right? There was never an atmosphere of hydrogen and oxygen and nitrogen. There was never that kind of environment. There wasn't people walking around breathing on the moon, except for the one time when they were. But the moon might have formed this way, right? This does not seem totally implausible, but it is very unlikely. It must not happen very often. And there's one big problem with this. This big debris cloud, or equally, this bizarre ring, would have what we would say is an infrared excess. Okay, more jargon for you. So when we look at the star's brightness as a function of its wavelength, right? So you take a prism and you break up the light as a function of wavelength. Here is the visible range. We've compressed it on this graph because it's boring. It's all normal. Again, a normal F-type star in the optical, visible, your eyeballs can see it light, and the infrared, i.e. What your remote control on your TV uses. In the far infrared regime, so this is very, very far, long wavelengths, dust glows. You glow, actually, in the infrared as well. And any plausible cloud of dust or debris or crap out here would be warm, and it would glow. And you wouldn't see it. It wouldn't be glowing bright enough to see it in the visible or even in the near infrared. But out here in the far infrared, you would expect to see this big bump in brightness, and we don't see it. We see this for other stars. We've seen this before. Now, we've never seen the Tabby star dips, but we've seen these kinds of excesses in the infrared. And we knew to look for it. It was one of the first things we looked for, and nobody saw it. So if there is this giant cloud of garbage out here, the leftovers from an explosion or an impact, you'd expect to see it. And we don't. These are what we call these upper limits. Like, these aren't detections at these various wavelengths. These are the sensitivity limits of our telescopes. Like, we can't see anything fainter than this at this telescope, and this telescope got a little fainter out here. So this is the one model we can't rule out, right? But it's not supported by the data. We can't rule it out. Okay, so we return back to this idea. Maybe it's aliens, okay? And like, the idea of aliens and SETI and UFOs gets a lot of flack in the astronomy community because oftentimes it's a lot of hyped up nonsense. But it is true that we do spend real money looking for aliens in astronomy, and we have to admit that it is possible, right? Anything that defies any other explanation, this has to be at least a contender for. Now, we were talking before the class, Occam's razor, right? Like, this would be unbelievably extraordinary, right? And so we would need extraordinary evidence, and we don't have it. There is this idea of a Dyson sphere. Okay, so the joke is that this is the Dyson vacuum. It's not related to Freeman Dyson, the scientist, but they both were British, so that's interesting. They're both still alive, too. The idea is the Dyson sphere is an alien civilization so advanced that they can build not just a spacecraft, but a ring or a sphere or some kind of funky shaped thing that totally surrounds their parent star. And by doing so, they trap all of that light. Imagine how much power a solar panel generates. Now put solar panels in a giant sphere around the entire star and capture every watt of energy that star emits. Okay? And once you do that, you have like unlimited electricity to do whatever it is that aliens do, right? I don't know. Watch Netflix in like 20K resolution or something. I don't know. But you have unlimited power to do whatever you want if you build this sphere, right? Because you've captured all the available energy from the star. Now, thermodynamics tells us that if you're cooking the inside of these solar panels or space vacuums with the starlight, you're going to need to radiate excess heat. Okay? Oh, here's a better, maybe this is a better explanation. Right? So this would be a Dyson swarm. Okay, so it's not a solid sphere. It's instead like some kind of grid or swarm of like solar panels or something around the star. Okay, whatever. The point is, we would expect that the excess heat, right, the thermal energy that's built up inside of that sphere would have to get radiated somewhere, or else it would just continue to get hotter and hotter unless they had perfect solar panels that were 100% efficient. And I just don't think that you can build a 100% efficient solar panel. Like, there's going to be some excess heat, right? My phone gets warm just like browsing Facebook. So their solar panels are going to produce some heat, and that heat would have to go somewhere. And again, we have the same problem. There's no excess heat here at the long wavelengths that we can see. Plus, why would you build your Dyson sphere to have this pattern, right? We would trace this pattern of fading events back to solar panels of various sizes moving into our field of view, right? As each one of these fading events comes and goes, that corresponds to one of these Dyson rings or a halo or something moving in front of your field of view. Why would it be shaped like this? And eventually, it would have to come back around, because that's how orbits work. you'd have to have a repeating pattern, and we haven't seen it. All right, well, that's a little depressing. It's not aliens, unfortunately, at least not to our best knowledge. So finally, what do we know? What productive things do we actually know? I've told you a lot about what it's not. All right, here's a paper that I wrote last year. This is the most ridiculous paper I've ever written because it was written about these 2 data points. So I was pretty proud of being able to write an entire paper about 2 dots. Here is the slow fading from Kepler that we showed you before, 3% fading. And here are 2 measurements that we were lucky to get by total chance in the ultraviolet. Okay, ultraviolet being the wavelength of light that your sunglasses filter out, and the atmosphere actually filters most of it out, because otherwise we'd just get sunburned constantly. So you need a space telescope to see the ultraviolet, because the atmosphere actually blocks most of the ultraviolet. We were lucky enough to get 2 data points in the ultraviolet during the Kepler mission of this star. And the punchline, and we can talk for a long time about why this is the case. The punchline is, if it's dust of some kind blocking the starlight, it's not normal dust. Normal dust blocks ultraviolet light really effectively. Again, our atmosphere blocks ultraviolet light really efficiently. Thank God, because that's how we manage to stay alive. Normal interstellar dust is this kind of stuff. Oh, okay, pretty pictures again. Here we go. This is examples of normal interstellar dust. The dusty lanes of the Milky Way itself, right? These little wispy lanes. If you go out to a really dark mountain, you can see this with your eye. It's like the most incredible thing. Go out into the mountains on a clear night, turn off all the lights for a half hour, let your eyes dilate in that no moon. Make sure it's a moonless night. And you can see with your naked eye this kind of wispy gas-like cloud structure. This is dust. We call this the galactic cirrus. These are clouds of dust. And they trace out the galaxy. This is normal dust. On smaller scales, this is a young star-forming region observed with Hubble Space Telescope. You can see tiny little wispy structures. This is a very small region where baby stars are being born. Baby stars and baby planets are being born. Tabby star, not inside of one of these. It's out by itself, out here in the galaxy, just wandering around like we are. But maybe there's wispy structure like this floating around it. Here is, I think it's called Barnard 68. It looks like a hole in the sky, like somebody just deleted all the stars. This actually is a dark gas cloud. If you look at this in the infrared, our friend the infrared again, you can see the little young stars hiding in here, emitting their heat. But in the visible light, the dust obscures the heat. That's pretty cool. This is normal interstellar dust. We know now that the ultraviolet, it blocked, well, whatever it was that caused the 3% fading, blocked some ultraviolet light, but not as much as you would expect. And that's one of the most scientific things to say. It's there, but it's not as much as we expected. Here is an actual map of the dust around Tabby star. I like they actually labeled it WTF. This is in the paper. I put a bigger star so you can see it, but this is where Tabby star is. And look, you can see this wispy, it looks like a radar map or something, of like a precipitation map moving through the northwest, right? And if this was Seattle, like this would be Olympia, and it'd be just like ripping through here, and we just get rain dumped on us. But like maybe that's the analogy, right? Maybe these clouds, these filaments of dust are moving through. Maybe they're really clumpy. Living in Seattle, you have an appreciation for how clumpy weather can be, right? It can be sunny 1 minute, raining 20 minutes later, sunny again, right? Like you can have large variations over small time scales, giving you some sense that like the size scale of these weather events or these clouds can be quite dense and small, right? Small, dense weather patterns can move through our area, dump a bunch of rain and be sunny, you know. I've seen days where it's sunny and snowing, right? It's unbelievable here. Maybe that's what's going on here. Maybe on very small scales, there are clumps of this dust, and it's weird dust, maybe. Okay, this is from 2018. This is a new paper. Okay, it's not a beautiful plot. This is not a beautiful infographic, but this is the 3% fading that we looked at again before, zoomed out, and a bunch of really crappy data they were able to dig out of a bunch of old archives, and a little bit of new data they went after to get. And they see, if you really squint, and i.e. if you're a computer and you can squint with the power of statistics, you can see there is some kind of slow, almost sine-like modulation here. Take my word for it, it's there. Maybe maybe this 3% modulation is repeating. Maybe that's some kind of structure outside. That's interesting. Here is another example. This is another 2018 paper. Here is that 3% modulation again. Here is maybe kind of a pattern. That's basically what the paper says. Maybe there's a pattern. They say it a little more positively than that. But I thought this was a really sick graphic. It came out a year ago. This is the idea that here we have all the short-term variations from the Kepler mission, and they attribute them back to some giant planet with some super duper Saturn with some tilted ring or something causing this asymmetric V. So this would be a transit, and that trailing and leading this giant planet would be asteroids, clouds of asteroids. Now Jupiter does this. Jupiter has what we call Trojans, these little asteroid clouds that are ahead and behind in some weird gravitational dance between the sun and Jupiter. They sit here in these funny little clouds ahead and behind. And maybe this set of dips that we saw here, and then the other ones that we saw, are clouds passing in front and behind. The idea is that the time between this set in here and this set in here was about even, roughly even. So maybe. This makes a strong prediction that in the early months of 2021, we should see these dips again. And May 19th, 2017, you should see this planet go around the backside of the star, and maybe you would see what we call a secondary eclipse, where the planet hides behind the star. And indeed, we did see a little bit of activity in May and June of last year, little 1% stuff. Not this, but little things. So we'll see, okay? So we'll see. In 2021, we might see a cloud of things move in front of Tabby's star again. Believe me, we'll be watching. From this new data, from that series of little dips we saw last year in May, we saw, okay, little tiny things that kind of look like, the gray line here is the Kepler data, that kind of look like the Kepler data-ish. And this is from the newest paper by Tabitha Boyajian, so this would be Tabby's star paper number 2, where she says, we're not buying this, but it's worth noting. This kind of looks like this, but there doesn't seem to be any reason. So maybe the short time scale modulations are repeating. And this, from her paper, I copied this today. Thus, the current evidence suggests that the short-term and long-term dimming events are caused by dust of some kind of different sizes. Dust of different sizes. I.e., you've got something close in and clumpy and weird forming the short time scale dips, and something large and diffuse causing the long time scale modulations. Maybe so 2 dust features. So here's my cartoon version of this. You've got something that's like, I don't know, a cosmic explosion or comet swarm or something causing short time scale dips as they move in front of the star. Maybe there's a periodic and we'll see them come around again. And you've got large fluffy clouds outside, maybe outside the solar system, the Tabby star solar system, slowly moving through, causing changes in the total brightness, like weather moving through Seattle. And this is kind of an explanation I can live with. Like, it's plausible. It doesn't seem totally Looney Tunes. We can go do some follow-up observations to see if this is actually periodic. We can do more observations to see if we can really see any infrared emission changing as these clouds move through. I can live with this explanation. But what is still bothering me, and what we're going to be working on here at the University of Washington for the next few years, one of the projects in the astronomy department we'll work on, is where are the other stars like this? Why is Tabby star the only star we've ever seen do this? We've looked at a lot of stars in the night sky. In the Gaia data release that came out last year, Gaia is a European mission, it came out last week. They released a catalog of 1.7 billion stars. And to our knowledge, none of those stars look like Tabby star, have done this kind of thing. We've studied the temporal evolution of stars here at UW over decades and never seen anything like this. So where the H is the other WTFs? That is the question that will drive some of my research in the next few years. And that's my last slide.